Hello. In the previous lecture, we looked at the Fourier transform, and let me just briefly recap the basic idea. So, we have a function. I imagine that it's a function that depends on time, so it describes some signal. You can think of a signal which is developing in time, or some data which is changing in time. And we would like to recover this function as a combination of certain oscillations, which are encoded using complex numbers. Okay, that's life. So here we have different oscillations, and we would like to specify how important each oscillation is, and according to the importance of each oscillation, put them together and recover the original function. Nice idea. Now, where do we get this information about importance of individual oscillations or individual frequencies? Well, here is the answer. We take a frequency omega, which is now a number, we fixed it. We are looking at a particular omega. And then we evaluate this integral in which omega is a parameter. So it's a constant. We just integrate with t. And because this is a parameter, t is a working variable. After integrating, we get a number which also depends on omega. Okay. So for each frequency omega, we get a number, and therefore we create a new function, which is this one. This is called the Fourier transform of the original f. So let's have a look at it from the other point of view now. We have a function, and using this formula, we create a new function, which creates a transform. From the world of functions which depend on time, we move to the world of functions that depend on omega, on frequencies. And there is a story for any given function representing a data. This function tells us importance of individual frequencies in our data. Okay? Very beautiful. And we found that there are some rules, there is some dictionary that actually allow us to change differential equations into algebraic equations, which is nice. But it turned out that the dictionary and the rules, they were not really convenient. That was the down part. That was what we didn't like. So here is an idea. Why don't I change this process of creating the new function, this Fourier transform? Why don't I mess with this formula a little bit, hopefully a little bit, so that we get nicer formulas? And it turns out that it can be done really easily. We just ignore this complex unit here, because let's face it, complex units are not really convenient when you are working with real functions. I mean, there is no reason to put some complex units when you are integrating, differentiating, whatever. So this brings us to our next definition. And as you can see, we are obtaining Laplace transform. That's the new idea. How does it work? You have a function f, and you create a new function which takes variable as a parameter. In our definition, it's called s now, not omega. And we are simply measuring the original function f, the data, against exponentials, exactly the same way that we did over here. This s now acts as a parameter, and we get a value. So this seems to be similar. And one might say, okay, so it essentially means that we are composing the original data out of some exponentials, but actually this is where it breaks down, okay? So the price that we pay for dropping this complex unit is that this story no longer works. It's not about recovering the original data from some exponentials. What we carried over is just this idea of using integral to create a new functions, but that's it. That's as far as it goes. So now it goes like that. We have a world of functions that depend on variable t. And using a specific procedure for each function f, we create a new function, and this new function lives in the world which uses variable s, traditionally. Some people use p, but I would stick with s because it's more widespread. Okay? Now this new function is called different ways. Let me just use one common notation, which is capital F. From lowercase, we pass to uppercase. Okay? Just like here from f, we are passing to f hat. So this is just a convention. The problem is that there is no such nice story that we had here for the Fourier transform. Here, if f is data, f hat is information about importance of frequencies. What is this capital F? I cannot tell you really a nice story about it. So this is not really pleasant. The Laplace transform becomes just a formal tool without a nice story behind it, but it doesn't mean that it's a bad tool. Okay? So let's have a look at how it works in detail. And we will gain some understanding, and then we will see what it is good for. So let's imagine, here is an example, that I would like to transform a function which is a constant function. Ft is equal to 1. That's a function. We know how it looks like. It looks like this. That's our f, t. That's important. And using the definition, hopefully, we can transform it into a new function. So there is this thing called Laplace transform, which is denoted like that, a nice script, capital L. And it changes into a new function, which can have different names, and we will get to it soon. For instance, capital F S, or it can be called Laplace transform of lowercase f with variable s. So capital F and this part, they are the same. They are equivalent. Okay? Now, what function is it? How does it work? Where does it send s as a variable? Well, for that we have a formula. So let's have a look at it. We take some s, and for this s we should get a value of our function, of the new function, of the Laplace transform of the original function. What does the definition say? It says integrate from 0 to infinity your function. Now my function is just a constant function, 1. Okay, here we go. I'm integrating 1 and multiplying it by e to negative st dt. So here s is a fixed number. For instance, if I want to know how much is capital F at 5, then I would take 5 and put it here. And I would be integrating e to negative 5t dt, which is a simple integral, no problem there. And if I want to know how much this capital F is at 13, I just grab 13, put it here, and I'm in fact integrating e to negative 13t dt. Again, that's a fairly simple integral. So how do I evaluate such an integral? Well, I introduce substitution, obviously. I take, okay, which way do I want to play it? This way. I take minus st, and I call it, I don't know, let's say u. I didn't use u for a while. Okay, let's work it out. Substitution. Let's see. Do I want to play substitution for the definite integral or for indefinite integral? That's a good concern. Let me play with the indefinite integral for a while, because we will see that there are some subtle nuances. Okay, this is u. So how much is the u? Let's remember, s is a parameter now, because it's a fixed number. I'm interested in what's happening for a particular s. So s is a constant, t is a working variable, so I'm differentiating with respect to t, and I get negative s, and I attach dt. If I decided to play with the definite integral, I would also have to change the limits. And this is where things would get interesting, because 0 for t changes into 0. That's nice. And infinity, when I put infinity for t, then u becomes negative s times infinity. And this is where it gets complicated, because we don't know what s is. Is it positive? Is it negative? Because it influences the outcome. So let's not worry about it, okay? I'm skipping this part. I'm just looking at the indefinite integral. Here we go. So my substitution says 1 is 1, I skip it. This is e to u. And then for dt, I have to substitute negative 1 over s du. How much is it? Well, s is a parameter. Did I notice? Did I mention it before? I think I did about 50 times. So I'm pulling out s because it's a constant, and I'm integrating e to u du. And this is where it gets nice. So negative 1 over s integral. Actually, I just did it. It's e to u. Now I'm going to introduce back the original variable. So it's negative 1 over s e to negative st. And this is the time when I recall that I actually was calculating a definite integral. So this is not proper mathematics. Perhaps I should do this part separately somewhere on the side and then return to the definite integral. Okay, so there is an interruption here. This part I did on the side or in my head. It's not here at all. Here I'm returning to my calculation. For t, I should substitute 0 and infinity. This is where it gets interesting. So, how does it go? Well. First of all, I have to substitute infinity, which is done using a limit. Improper integral. Limit t going to infinity, negative 1 over s e to negative st. And then I'm subtracting, and I put 0 for t. E to 0 is just 1. So I'm subtracting negative 1 over s times e to 0. Let me put it like that so that people can see what I did. I substituted 0 for t. Okay, now, how about this part? When I send t to infinity, then everything depends on the sign of s. If s is negative, then I get infinity, negative number, negative sign gives me plus infinity, and this whole thing blows up. So this is the moment when I don't want to see negative s's, and also I don't want to see 0. So at this moment, I decide, out of the sense of self-preservation essentially, that I want s to be positive. And then infinity times a positive number is infinity. With minus, it's e to negative infinity, this is 0. And then there is plus 1 over s. And I'm getting 1 over s. What did I just do? Laplace transform takes a function and changes it into a new function. How does this new function work? It takes a variable, looks at some value, let's say 5, and I find that for s equal to 5, my new function gives me 1 over 5. And if I want to know how much f is at 13, I put here 13 for s, and I find that the outcome is 1 over 13, and so on. For every number, for every variable s, new variable, this function changes it, sends it into 1 over s. So the formula actually reads fs is 1 over s, or Laplace transform of lowercase f at s is 1 over s. For s greater than 0, I have to be careful. So, what is really happening? This function, the constant function 1, changed into a new function, namely the function 1 over s. And let me add number 1 here. So the Laplace transform takes this function and changes it or sends it to this function in this other world. Okay, so here is the function 1, and it gets sent to function 1 over s for s positive. Okay? Interesting. Now, can I invent some story which would tell me intuitively that this is the right outcome? And the answer is not quite. I cannot really tell you a nice story that would allow me to just look at this f and say, oh, Laplace transform will be this. So that's a little bit of a disadvantage for the Laplace transform, but you can see its main advantage. This is actually nice. From function 1, I'm getting function 1 over s. That's a cute function. If you compare it to the original Fourier transform, this is way, way more convenient. And that's the beauty of the Laplace transform. Perhaps it doesn't have a nice story behind it. Okay, we can live with that. But it's practical. It's nice. Okay, it's convenient. Let's have a look at a few other functions to see how it goes. So let's make some room. In our next example, we will be curious about a function ft is equal to t. So again, if you want to see it graphically, this is our favorite diagonal linear function. And we are wondering, okay, I take the Laplace transform, and this function gets sent to some other function. Here is t, and it goes somewhere here perhaps. What is the formula for the new function? Well, let's have a look at it. How does the new function look like? We are interested in the value of this new function at a specific s, so we should evaluate integral from 0 to infinity. Here we put our function f according to the prescription, which is t, and then e to negative st dt. And again, s acts as a parameter because it's some particular number which I'm putting here. Okay? Well, what can we do with that? Substitution. Here we go. U is negative st, du is negative s dt, and let's play with the definite integral. Let's make it proper. So when t is 0, then u is also 0, because I'm putting 0 for t, and this becomes 0. When t is infinity, this is where it gets interesting, then let's skip the discussions that we had before, because we know what's going to happen. So let's just proclaim at this moment that s is positive. Okay? This simplifies my life. T is infinity, s is a positive number, so that's infinity, and u will be negative infinity. Here we go. Everything is clear. So my new integral goes from 0 to negative infinity. Now I have to substitute for t. How much is t? That's a good question. Here is my formula. T is actually negative u over s. Okay, I can live with that. Then there is e to u. And then I have to put dt in the formula, and dt is negative 1 over s times du. Okay, so far so good. What do I see there? I see two minuses, they cancel, fine. I can see s squared, s is a parameter, it goes out. Nice. And then there is the integral between 0 and negative infinity, taken from u eu du. Wow. Okay. Can I handle this one in my head? The answer is no. I still have to do some work. So what do I have to do? I have to use integration by parts. Here we go. 1 over s squared, and then integration by parts. How does it go? Okay, I have to decide which of these guys will be integrated, which of these guys will be differentiated. Well, obviously this one will go down. I will differentiate it to downgrade it. And this guy will go up. I will integrate it. That's how I feel about it. One goes down, the other goes up. So the formula for integration by parts. Now, of course, you want to do it properly, so you write it down. I mean, there was something like that, if I remember correctly. Some people use udv, but then I get a mess with this part, so perhaps I'm going to use f and g, and f will be e to u, g prime will be u, or the other way around? The other way around, of course. U, it's been a while since I've been doing it, because I always do it in my head, you know. So if you want, you can go like that, play with it, do the integration by parts exactly the way you prefer it, okay? I prefer to just look at it and do it. So, okay, first this guy goes up. I get u e to u, and this is taken from 0 to negative infinity. Then I put minus, and I repeat my integral, and this guy went up to e to u, and this guy goes down to 1, du. That should be it. Okay, I look at it and I say, wow, that's nice. I can handle that. 1 over s squared. Now, I'm substituting negative infinity into u e to u, which essentially means I'm taking a limit. And again, you can, you know what? Side note. I'm sending u to negative infinity, and I have u e to u. I make another substitution, v is equal to negative u, and it becomes a limit v going to plus infinity, that's important, v with minus e to negative v. So this is limit v going to infinity, negative v over e to v, and we all know that this is 0. Because at infinity, exponentials beat powers. Easy. So when I substitute negative infinity here, e to negative infinity is 0, and it is much stronger 0 than infinity here with u. It becomes 0. I substitute 0, everything becomes 0. That was easy. And now I integrate over here. I'm integrating the exponential, so it will be e to u taken from 0 to negative infinity. And we are finally getting there. So 0, 0, no problem there. I'm subtracting e to negative infinity, so I'm subtracting 0. And then I'm subtracting and subtracting. OK, let me put it like that. I put 0 here. And when all is said and done, this is 1 over s squared. OK, so it was a little bit longer. I admit that. The previous calculation was a little bit neater. But yeah, I mean, integration by parts is routine for those who passed calculus course recently. And substitution also nice. Review of... This is like a review of calculus. OK, almost everything is there. Anyway, here is the bottom line. When the function ft is equal to t, a linear function, is transformed by Laplace, it changes into function capital Fs is 1 over s squared, or Laplace of t, when applied to s, is 1 over s squared, s positive. That's a nice way to put it, like that. Laplace of this function. Yeah? It tells us exactly what's happening. OK, t goes to 1 over s squared. Now, if you're curious about t square, how about the function t square? Well, you just follow the same path, and integration by parts would have to be done twice. Yeah, it works. No big deal. It's just longer. So I'm not going to do it. Instead, I'm going to try this baby. The last example of this sort. What's our favorite function? Well, the exponential, of course. So what happens if I try to transform exponential as a function? T over here, my favorite. Perhaps I should emphasize t over here, and perhaps I can add 1 over s squared, looks like that. Okay? This shape changes into this shape. Why? Again, as I said, I don't have a nice story about it. That's life. So now we have this shape, a function. I now see the function not as a process or something, but as one thing, as one object. This object changes under Laplace transform into another object. What kind of object is that? Well, again, let's have a look at it. I take some s, some value, and I ask, this new function over here, fs, what will it do with my variable s? Where will it send it? I go to the definition. I'm integrating between 0 and infinity my function, which is e to t, multiplied by e to negative st dt. Wow, that looks easy, doesn't it? OK, let's see. First of all, I'm going to unify the exponentials. This is e to t times 1 minus s dt. Now, I use substitution, or if you're experienced, integrator. You can do it in your head. After all, we have done this substitution here several times. This is just a product substitution. So this is easy. I just imagine that there's number 5. I mean, everybody can integrate exponential if there is 5t, or 15t, or 150t, whatever. This constant simply drops down. So it drops down. And then we will have this exponential in our integral, in our antiderivative, to be more precise. And we integrate from 0 to infinity. Here we go. And as before, we have to apply limit to obtain the first part of our result. So we are sending t to infinity. inside the limit, we have this baby. And we are subtracting. And here we put 1 over 1 minus s times e2. And we put 0 for t, e to 0. That's really nice. And again, here we have to sort of think about stuff. Okay, 1 over 1 minus s, that's a constant. No big deal. T goes to infinity. This is the place. We have infinity here. And if I want this limit to be nice, I would actually prefer to have negative infinity here. So again, what we are going to do, we are going to proclaim that we are not interested in all s's, but only in those s's where 1 minus s is negative. That's what we really need. So, if 1 minus s is negative, then infinity times a negative number is negative infinity, and this whole thing is just 0. And then we are subtracting 1 over 1 minus s, and the answer is 1 over s minus 1. That is the outcome. Let's see. 1 minus s is negative. What does it mean? Well, I move s to the other side. I'm interested just in s's larger than 1. So, we just learned that when we start with the exponential as our original function, and we transform it using Laplace transform into this other world, into the world of functions that work with s, here is e to t, then the outcome is a function 1 over s minus 1. So the function e to t is sent to function 1 over s minus 1, or I could also write it like this. Laplace transform of e to t is 1 over s minus 1, but with the condition that s is allowed to be larger than 1 only. It doesn't work elsewhere. So here is a picture, here is s, here is number 1, 1 over s minus 1. I believe it looks like that. And for some reason, well, I know for which reason, for the reason of the definition. The definition causes the exponential change into, or be sent to, or be transformed into this function. Yeah? Okay, so as you can see, we are getting a dictionary, which is quite convenient. From this function, we get to this function. I mean, we can see it here in this picture. Okay? The Laplace transform is transforming functions, nice functions, into nice functions. So this looks like a very convenient transform so far. Before we look at the dictionary, let's ask some good mathematical questions, questions that we sort of skipped when we were looking at the Fourier transform. But now, because we want to use this one heavily when solving differential equations, we should do a little bit more of proper mathematics. So, first of all, what kind of functions is the Laplace transform capable of handling? Okay, so we look at the calculation. Our function ft appears here, and then we are doing some integration, stuff like that. So the first requirement is that this integral should be actually existing in the mathematical sense. It should provide us with an answer. So this function should be integrable. That's the baseline requirement. Now, exponential is a continuous function, so this does not cause any trouble. If this function f were continuous, then again we do not have any trouble, which is exactly the case of our examples. Okay? These were all continuous functions. But it will turn out that this is a little bit too demanding. We would love to do or to apply the Laplace transforms also to functions that are not quite continuous. There will be some discontinuities, but we cannot afford to have too many of them, because if you have a function with too many discontinuities, you cannot integrate it. That's one of the facts from calculus course when we were doing Riemann integral. So, if we want to integrate, we have to restrict our attention to functions with discontinuities, but with just few of them. And the best thing you can do is to take functions which are piecewise continuous. So you have a function which exists where? That's a good question. Well, you actually just care about the interval 0, infinity. So you look at interval 0, infinity. And you should be able to split it into intervals finitely many intervals. If you allow for countably many, you run into trouble. You have to be careful how you choose them, okay? But anyway, there is a precise mathematical definition that we don't have to really worry too much about. At this stage, it will be enough to just imagine finitely many intervals, and on each of these intervals, our function should be continuous. What happens at those endpoints? The answer is I don't really care. Perhaps at this point, the value could be here, or somewhere in between. I'm not really worried about it. Everything will be fine. Well, this is actually continuative from the side. So here I could say in mathematical language that a function is continuous from the left. Here it's continuous from the right. Here it's continuous from the left. Here it's not continuous at all. Not from the left, not from the right. So a function like that would work in my integral when it comes to integrability. But the problem is that I'm also integrating all the way to infinity, which means I have to worry about the function having too much area under its graph. I don't want this indefinite integral to be infinite, which is exactly why I was restricting my attention to only specific s's. But how do I do it in general? Well, two components here. One component is e to negative st. If s is positive, and we can always arrange for that, no problem there, then we are integrating the usual exponential, but with a negative sign here. So what is really happening there, we have a function that looks like that. And we know, and this is easy to check, that you can integrate this function from 0 all the way to infinity. No problem. If you multiply this function by a constant, it will still work. The infinite integral will never diverge on you. If you multiply it by t, which is what we tried over here, then this exponential multiplied by t, okay, t goes to infinity. It's a growing function, increasing function. So you take this nicely decreasing function and start multiplying it by increasing function. So those two tendencies will be fighting each other for a while. But it turns out that the exponential eventually wins, and everything ended up well. We didn't have any trouble with convergence. So we can actually afford this function, the first component, the component f, to be constant or perhaps increasing, but perhaps not too fast, because if I put a function here, f, which increases too fast, then it will overwhelm this decreasing exponential, and I will get in big trouble in my integral. When you go all the way to infinity, you get infinite area, and you are really in big trouble. So, if you want to be on the safe side, we have to somehow say that the function f here shouldn't be growing too fast. Now notice that our function is actually growing reasonably fast. It grows as fast as exponential. So here we have an exponential which falls down at exponential speed, and we multiply it by a function which grows at the exponential speed. But those speeds, they somehow sort of, cancel each other. If I look to the right far enough, I'm fine. That's the condition. So this is sort of like a borderline of what we can safely afford. If we allow a function to grow even faster than that, then we can no longer rely on things being nice. So this is exactly what we will do. This will be our requirement. When we are doing the Laplace transform, we are just looking at functions which are piecewise continuous, and they don't grow faster than exponentials. And when we do it like that, we get a very nice space of functions where the Laplace transform actually works. So we can imagine that here, this set, these are functions which have these properties. They don't grow too fast, and they are piecewise continuous. Okay? So here is a definition. This is traditionally called L0. I can put it here now. The definition says, these are functions which go from 0 infinity to r, piecewise continuous, and there is a bound, upper bound, using some exponential. Wonderful. This is not the whole story. You see, when we are doing this Laplace transform, we never care about negative t's. So we don't really need to have any value for negative t's with our functions f. So we don't really care what's happening over here. We don't really care what's happening over here. which is what the definition L0 says. We are just looking at functions from 0 to infinity. So we are, in fact, over here, working with restrictions. We are not really transforming e to t, but we are, in fact, transforming this function. And writing it down mathematically as a restriction wouldn't be really convenient. So there is a little trick. But it's also philosophical. It will be helpful later on if we sort of did have information about what's happening on the left. Namely, it would be to our advantage if we assume that all functions that we are transforming are just 0 here. And 0 means that we ignore it. So people have sort of like two different points of view. Some people just look at interval 0, infinity, and they do not worry about anything else. But then it sort of becomes troublesome later on. Or you can start by saying, OK, I just care about the values from 0 to the right, and I'm going to assume that everything from 0 to the left is 0, all the values of my functions. Okay? So this set L0 may be seen just as functions on 0, infinity, or it may be seen as functions where the interesting things are happening between 0 and infinity. And over here, all those functions are 0. This can be arranged using a very smart mathematical function. Let me show you a definition. This is called Heaviside function. And by the way, it's not a misprint. This Heaviside dude, he had two i's. There is no y. Especially the first one is I, not y. So this is Heaviside function. And when you look at the definition, it looks like embodiment of this idea that our interest lies only in specific place. So the Heaviside function looks like this. It starts at 1, and it remains 1. And on the negative half-axis, it's 0. This is the Heaviside function. Now, why is this useful? Well, let's go back to this picture. I have an exponential, so I have some information also for negative t's, but this information is useless. I don't want it. Instead, I want to take this information and change it into 0 so that it doesn't interfere with some stuff which will come later. How do I achieve that? Well, this function is actually the exponential multiplied by the Heaviside function. Is that right? If t is 0 or more, then the Heaviside function is equal to 1, and yes, we do have the exponential here. If t is negative, then the Heaviside function is 0, and it kills off this exponential. We get 0. Wow, it works. How about here? What happens if I take t and multiply it by the Heaviside function? Well, when t is positive, Heaviside function is 1, and I recover this nice diagonal shape. If t is negative, the Heaviside function is 0, and I get this. Exactly what I want. So many authors, when they are transforming functions, they automatically put the Heaviside function next to them to emphasize that they are ignoring the negative part. They are considering it to be 0. And many authors, they do so as well, but they don't write it. They just consider it automatic. So essentially, in the Laplace transform, every time you see a formula for transformation, you just assume that this original function was killed on the negative real line. The values are 0, automatically. This can be also used to do some little tricks, neat tricks, and I'm running out of room. So, a little finishing note about the Heaviside function. Let's imagine that we have a formula, some function that we like, some elementary function, and we multiply it by the Heaviside function. People had an interesting idea. Evaluating Heaviside function could take precedence over evaluating ft. So we start here, and if necessary, we go here. This is an interesting consequence. Imagine that you have the function square root of t. Now, square root of t, as we all know, exists only for t greater than or equal to 0. What happens if I write square root of t times the Heaviside function? Well, when t is positive for 0, Heaviside is equal to 1, and we get this. when t is negative, then the Heaviside function is 0, and there is no point in going on with evaluation because we know that it's 0. And we get something like that. So in fact, the Heaviside function allows us to create a function which is defined everywhere on the real line. It's 0 on the left part, because that's what we want for the Laplace transform. And we get a nice function that can be included in our space L0. We can do the Laplace transform. By the way, if you try this calculation, it's beastly, okay? So don't ask me what is the outcome. You don't want to know. Anyway, let's have a look at things that we do know and talk a little bit about notation. For instance, we found that function 1, constant function, changed into 1 over s under the Laplace transform. So how do we write it? And there are quite a few ways. One way that we saw is that when the function ft is 1, or perhaps function ft is 1 times the Heaviside function, and this is actually what we used, and this is what people often write because they're lazy, okay? Then capital Fs is 1 over s as positive. Now, this is a nice notation in certain situations, but there are moments where we would prefer something more brief, because those f's over here, they are not really needed. See, they are wasteful. You have two different letters here expressing something which actually just works with two ideas which are over here. You don't need f's to connect these two ideas. Perhaps there is a better notation that does it without f's, and the answer is, it looks like this. No, I'm messing up. Okay, I said it nicely the first time and I used the wrong notation. Okay, that's life. I have to get into the flow again. Into the flow again. Okay, here we go. Now, this notation is very convenient in certain settings, but generally speaking, it's a little bit wasteful, because what we really want to show is that this function goes to this function under the Laplace transform, and perhaps we do not need to introduce two letters for that. Perhaps we can do it somehow directly. So here is an alternative. You have a function 1, and when you apply Laplace transform to this function, you get a new function. How does the new function look like? Well, first of all, it has a variable, namely s, and at this s, the function has the value 1 over s, for s positive. It's the same message, just in a different way. Or perhaps you can be a little bit, let's say, more conscious, you can do it more properly, because this is the lazy people's version, which is why you will see me doing it quite a lot, because I'm lazy. But properly, what we should write is that Laplace transform of 1 multiplied by the Heaviside function at s is 1 over s as positive. Now, if you take a function and you multiply it by 1, we are not really changing it. So what we also did is this, that the Laplace transform of Heaviside function itself is 1 over s as positive. Wow, that's neat. These two notations essentially say the same thing, because Laplace transform only cares about what's happening from 0 to the right. And when you look at those two functions from 0 to the right, they are the same. So the Laplace transform must have the same outcomes. Okay? Makes sense. Now, you say, okay, this is nice, it connects the two functions, but perhaps too many symbols, yeah. Too many characters that I have to write, and especially these roundish brackets, whatever these composed brackets, they take a while. So is there something neater? And the answer is, how about this? Function 1 is transformed into function 1 over s. Wow! Function 1 times Heaviside is transformed to 1 over s. Heaviside function is transformed into 1 over s. And that's essentially the best notation you can have, the most convenient, but it only allows you to sort of do one-step calculations. It's really hard to use this notation, this type of writing, and do something which is longer. a multiple step calculation. For that, this notation is actually preferable. And it can be also done using this notation, but with the, I will show some examples. You will see it soon what I mean. So these are the most popular ways to express that the Laplace transform changes functions in a specific way. Okay? You either introduce little lowercase f, and then the Laplace transform creates uppercase f, or you use these two types of notations. So we are ready now. Let's introduce our first dictionary. On the left, the long notation, and proper, including heaviside functions. On the right, brief notation. We even skipped S positive and so on, because people very often do it. When they go for brief notation, they sort of consider this to be automatic or that everybody knows it. But perhaps that was an error. Anyway, on the left, let's have a look here. We know how to transform exponentials. We know how to transform powers, sine and cosine. Where did we get the result for sine and cosine? Well, perhaps we expressed sine and cosine using exponentials, complex exponentials, and then we put it together using linearity. We will talk about it soon. So there are ways. There are ways. The first formula, e to alpha t, well, that's essentially what we did before. We did e to t, which is e to 1 times t. And the calculations with e to 2 times t would be exactly the same. We just used substitution and it worked out. So the first rule we essentially proved when we are proving the rule for e to t. The second rule, I commented on it. You have to use integration by parts n times, and it's boring, but it can be done. Here is an interesting point. You may have noticed that when we are transforming 1, we got 1 over s, and for e to t, we got 1 over s minus 1, which is remarkably similar. So one thinks, okay, is there perhaps something to it? Now, when you look at these two formulas, it's quite obvious what's happening. How do you get a constant function 1? Well, one possibility is that you take the exponential, rule number 1, and you put alpha equal to 0, because e to 0 times t is just 1. So when you put alpha equal to 0 in the first formula, you get 1 over s. Voila. It's a special case of the exponential. Or you can get 1 as t to 0, which is rule number 2. If you put 0 into the second rule, you get 1. So 1 over s is like special case of these two rules in a way. Okay? Notice that in the second rule, n cannot be negative. We don't know how to transform 1 over t because we get immediately into trouble. If you try to transform 1 over t squared, there are problems at 0, because at 0 those functions go to infinity, 1 over t. They create divergent integrals, lots of trouble. We don't worry about it. We don't play with it. It's not our favorite toy. So we stick just with polynomials, essentially, with powers. Okay, so these are rules that people who use Laplace transform memorize by heart. They just know them and apply them easily. But sometimes you need to transform also some other functions, and then it helps to know some grammar. So here is our favorite grammar for the Laplace transform. And as you can see, it's given in the scriptal language, because these rules are often used for manipulation of expressions, and this sometimes takes a while, so it's good to have this notation. In particular, it allows you to delay some steps, which is convenient. We will see some examples. So let's have a look at those rules. Let's start number 1. It's called linearity, and indeed it is linearity, because L stands for Laplace transform. It is a mapping, and this mapping, as a mapping, when you look at it through the eyes of linear algebra, is linear. That's exactly what the rule says. So let's say when you have two functions in your original space, you have two choices. You can add them in the original space and send this outcome over to the other side, using Laplace, or you take the two individual functions, you send them over, and you add them there. Freedom, choice of two, nice. How do we prove it? The answer is easily. Laplace transform of aft plus bgt, and now these are two functions that belong to the space L0, and we should actually show that the linear combination also belongs to L0, and this can be done relatively easily, so I'm not going to waste our time on it. But when we do it, we are actually showing that the space L0 is a vector space, it's a linear space. So you can combine functions from this space in this way, you can form linear combinations, and you are still within this space, you don't jump out, which is nice. We can also imagine that the formulas for ft and gt include the Heaviside functions, so they are 0 on the negative half-axis. Okay, this is a new function, it has variable s. And the definition says, if you want to know how much this function is when you substitute some s, you just evaluate an integral from 0 to infinity. Here you put your function, aft plus bgt, multiplied by the exponential, well, it's gone, but I remember it, dt. And we are using s as a parameter. Well, let's have a look at it. I multiply out, and I get a ft e to negative st plus b gt e to negative st dt. I can split this because we know that the integration is linear as well. A integral 0 to infinity ft e to negative st dt. This is getting boring, isn't it? Perhaps I should invent some sort of a stamp, and I would be just stamping this. Or copy-paste capability for my blackboard. Anyway, this is A. This is the expression which tells me what is the value of the Laplace transform of f when I look at it at S. Laplace transform of f when I look at it at S. Did I put t here? Perhaps I should put t here. Let me squeeze a little t here. Talking about laziness, sometimes people skip t. They just write Laplace g. It works. Anyway, that's the rule. Now, when we are working with functions, sometimes we do not write the argument, and that's the shortened version that we see on the slide. Okay? So sometimes you just write f, sometimes you write ft. The same idea. Okay? The second rule. Let's have a look at the second rule because it's useful. Here we go. First, let's try to interpret it. On the previous blackboard, I proved the formula for the Laplace transform of the exponential e to t. So this is something that we know. What if we want to transform e to 5t? Well, we could derive the formula again, or we could use rule number 2, because rule number 2 says you have a function f, and you introduce some constant, some multiplicative constant into its argument. So instead of e to t, I have e to 5t, or e to 8t. Okay? So that's introducing a multiplicative parameter there. And if I want to know how the Laplace transform looks like, it's actually enough to transform the original function. That's what we see on the right. And after you transform it, you should do some modifications. You should divide it by a, and on the right, that's a shortcut, that's a favorite physical shortcut for delayed substitution. So let's have a look at it in detail, and we will see how it works. So I have a function f, and I decide to multiply the argument by a. So it's a scaling, horizontal scaling of my function. Now I want to transform this function using Laplace transform, and then I want to substitute some s, and I'd like to know what is the value. So again, let's have a look at the definition. Integral 0 to infinity, I'm transforming function at, and the rest is prescribed in the definition, so there is nothing I can do there, or nothing creative. I just have to write it down. Okay, now this is becoming interesting, because normally, if I were evaluating it, I would do substitution here to simplify the exponential. But in fact, I'm not evaluating it because I don't know f. So I cannot actually calculate the outcome as a number or something with s in it. Rather, I'm trying to change it into something that I know. And what I know, that's my assumption, I know how to handle ft. So I'm going to use a different substitution this time. I take at and I give it a new name. Well, t is gone, s is gone. U has been here in a different role. How about v? Okay, v. A is a parameter. T is my working variable in my integral. So a dt is dv. A is positive, I think. Let's have a look at it. Yes, A is positive. This will be important. Why? Because I'm going to also change the limits. So when t is 0, then of course v is 0. That's easy. When t is infinity, then because A is positive, let me remind myself, A is positive, then also v is infinity. Infinity goes to infinity. So the limits are actually preserved. That's nice. Here I have fv. Now, in this exponential, I have to replace t. How much is t? T is v over a. And for dt, I have to replace from here. dt is 1 over a dv. Okay. 1 over a goes out. That's obvious. Integral 0 to infinity fv e to negative s over a v dv. Now remember, in this integral, in the definition, t is just a working variable. So if I replace t with another letter, it will still be Laplace transform formula. If you feel uneasy about it, make a new substitution and just replace v with t, which means erasing v and putting t in its place. Okay? This is in fact a formula for the value of a Laplace transform. Laplace transform of what? And the answer is of the function f, because this is the exponential and this is the function f. So 1 over a Laplace transform of the function f, but the original function without any multiplication here. It's just a variable here, which we traditionally call t. And now I'm substituting something. And what I'm substituting can be found over here. I substituted s, so it made its way over here. I'm substituting s, it made its way over here. I'm substituting s over a. How do I know that this is right? I could try to go backwards. 1 over a goes to 1 over a. How do I find Laplace transform of ft? Well, I take ft and I put it here and I attach exponential. What is in the exponential? The working variable. And then there is the number which I'm substituting. I'm substituting this number. It all fits. Okay? And that's the formula. And this substitution, which you do at the end, first you do the calculation, and when you have the outcome, you substitute. So this, in physics, they often denote like that. Or sometimes they write S is equal to S over A, or something like that, or, you know. So, and that's rule number 2. Rule number 3, equally easy to prove. Rule number 4, integration by parts. Not very pleasant, it can be done, and so on. We can go through all the rules. Most of them are relatively easy to do, and they all have the same idea. For instance, let's have a look at an interesting rule, which is over here, number 5. Number 5, this is what will be interesting for us. I have a function, and I want to transform it, but actually not this function. I want to transform its derivative. So what is the value at some s? Good question. Definition says, take integral from 0 to infinity, put your function in it, the one that you are transforming, of course. Attach this exponential Just copy-paste and work it out. Okay, fair enough. Again, I don't want to evaluate because I don't know f, so how can I evaluate without knowing f? Instead, I'm trying to change it into something that I do know. In other words, I'm really bothered by this derivative. I would really love to get rid of it. So what I'm going to do, I'm going to use integration by parts. But this time, I'm not going to differentiate here, but integrate. So this part will be integrated, and this part will be differentiated. That's my plan for integration by parts. So let's have a look at it. This is the part which is already finished. I'm substituting 0 and infinity. And as I said, I'm going to integrate here. And this part is just copied in integration by parts process. Then I'm subtracting integral from 0 to infinity. This part was integrated. And this part will be differentiated with respect to t. That's important. So by the chain rule, I differentiate the exponential. Then I put times. And I differentiate the inside function with respect to t. So negative s drops down, dt. Okie dokie. I'm substituting two things here. And I have to work it out somehow. So let's have a look at it. First infinity. I put limit t going to infinity ft divided by e to st. So far, so good. Minus. I'm substituting 0. What do I know about the function f? Well, not very much. I just know that it's piecewise continuous. So I don't know that it's continuous at 0, and that's why I have to also use limit t going to 0 from the right, ft divided by e to st. Why did I write it as a ratio? Because I feel better what's happening there. That's important. When you are doing limits, when you are evaluating limits, it's good to have some intuitive idea of what's happening. Let's move on. Minus and minus give me plus. S jumps out because it's a constant, it's a parameter. That's the value of argument that I'm interested in, a concrete number. And integral 0 to infinity ft e to negative st dt. Okay. Let's start from the easy part. I look at it and I say, I've seen that one before. That's the basic integral for Laplace transform. I'm interested in value s, and I want to know what is the value of Laplace transform of this function. Yes, Laplace transform of this function evaluated at s. That's what the integral tells me, and it's multiplied by s. Minus, when t goes to 0 from the right, this is a continuous function. T goes to 0, e to 0 is 1. But what we don't know is the value of this when t goes to 0 from the right. That's simply a limit. And for this limit, we have a shortcut. That's the shortcut for the limit. And we can see that in our formula. So the first part, it fits. S Laplace of f. Then we are subtracting f at the 0 from the right. That's a shortcut for limit. And we don't multiply by anything. And according to rule, we should multiply by s to n minus 1. But in our case, the number of derivative is 1. N is 1. So things disappeared. When you look at the next terms, we are again looking at the values of f and derivative of f and so on at 0. So these things appear when there is higher derivative. If you have a second derivative, you have to do integration by parts twice. And there will be two limits like that. And if you have third derivative, you have to do integration by parts 3 times. And there will be 3 limits like that. So that's the tail. But notice that the tail does not involve Laplace transform at all. You are just looking at the original function, how it looks like at the origin. So this is okay. then there's this limit. And this one is a little bit troublesome. One has to do a little bit of argument. E to st, okay, s is positive. Definitely s is positive. So this one goes to infinity. This one could also go to infinity if we are not lucky. So these are two infinities competing, but the trick is that f is from L0. L0, these are functions that can be bounded by a specific exponential. This guy can go to infinity, but it has to be below e to some number times t. But here I can make s really large. I can make this exponential stronger. So I can argue this requires a little bit more. So I'm skipping on some details here. I can argue that this is 0. So this is an almost proof. I skipped over some details, but I think it shows the main message. So here is the rule for the first derivative in the script L notation, the long notation which is good for long calculations. Interesting question. Can we express it somehow using our shorter notations? And the sad news is that we cannot do that. We cannot express grammar using equality with hat. You remember the previous slide over here on the right where we didn't have to introduce any f or anything, and we didn't have to use script L. We just simply connected two things together using the special equality. Now this cannot be done to express our grammar rules, like linearity, this thing, rule for derivative. That's unfortunate. But what we can do, we can actually introduce lowercase f, uppercase f, and then these rules, they look sort of like easier, which is, of course, just impression, but it's sometimes helpful. So here is the idea. You have a function f, and you know how to transform it into some other function. This is the notation. So let's say that you know how to transform exponential, or sine, or cosine. So the outcome will be here, denoted with capital F and with variable s. And you ask, okay, if I know how to transform little f, can I perhaps transform FAT? And the answer is yes. If you know how to transform just f, then FAT is transformed as 1 over a. Then you do the Laplace transform of little f, but you know how to do that. That's your function capital F. And you substitute s over a. So these two lines together, they express this rule. So you either need just one line with script L, and it looks complicated, or you need two lines, and it sends the message in a way, perhaps in a clearer way. Let's have a look at this rule. Again, I need two lines. First, I need this introductory line, which says, I have a function, and I know how to do the Laplace transform, because I'm good. And then I can also transform the derivative. And if I want to transform the derivative, all I need to do is to take the transform of the original function, which is what I can see over here. That's a transform of the original function, multiplied by s, and subtract this value at the origin of the original function. Okay? So that would be the alternative expression for my grammar rules. And it's, let's say, it's more concise in a way. And this is fairly useful for quick calculations. For longer calculations with many steps, I personally prefer script L. But there are people that can handle it that way as well. Okay? So let's have a look at the list of what we figured out so far. So this is a brief version, short master list. On the left, we can see the dictionary. On the right, we can see the grammar rules, those that are very important. They are not all the rules that we had previously. These are the rules that people use most often. For instance, we don't care about the 15th derivative. Typically, we just transfer the first and the second derivative. And you can see the rules here, and they correspond to what I just wrote. Okay? On the top, there is the rule for linearity. And it assumes, I didn't write this line, but I should have, perhaps. It assumes that you know how to handle f, and you know how to handle g in the first rule. Now, to appreciate these rules better, and to understand the notation better, let's have a look at some examples. So let's say that I would like to transform function t times e to 3t. And in fact, I should put ht there as well, the Heaviside function. But as I said, people usually skip it, so I'm going to skip it soon. Okay. How do I transform it? Well, definitely this function, t times e to 3t, is not in my dictionary. But if I ignore t, the exponential is there. If I ignore the exponential, t is there. So it's essentially a function that I know modified in a certain way. So I look at my grammar, and many rules are actually of this form, that I have something that I know modified. So I look at number 3, which is called shift in the image for some reason. We will see why. And it says what to do when you are transforming a function ft that you know, multiplied by some extra exponential. So that's exactly what we are going to do now, using rule number 3. And the rule says, do the Laplace transform applied to your original function without the exponential. So what I should do is to apply Laplace to this without the exponential. Okay, I put Heaviside there. And when I'm through with that, I should substitute, that's the delayed substitution, s minus a, where a comes from this exponential. So I should substitute s minus 3. I just applied rule number 3. Okay, let's work it out. How much is Laplace transform of t? Well, that's my dictionary. Let's go back. Laplace transform of t is t to 1, so it's 1 factorial, divided by s to 1 plus 1, which is s squared. Well, actually, it's over here. I calculated it directly. So this is the Laplace transform of just t, and I should substitute delayed substitution. You see, I was supposed to substitute here, but I didn't have any place to substitute it into because I didn't know the outcome. Now I know the outcome, I can substitute, and the answer is 1 over s minus 3 squared. S greater than 3. Here we are. We are done. Wonderful. Let's try the same thing using the f notation. So, I go to this list. Now we have to look at rule number 2 on the right. So we are assuming that we know how to transform little f. So it goes like that. I know how to transform ft, which is t, into capital Fs, which is 1 over s squared. This is what I know. And the rule says, if instead of your f, you want to transform e to 3t and your function, then you simply take your capital F, the one that you have here, and you substitute s minus 3, which is 1 over s minus 3 squared. We are done. Okay? So this is the main idea of those grammatic rules. You know how to work with f, and then you know how to work with modification of f. And modification here influences or creates modification here. A different modification, as you can see. If you attach an extra exponential to your original function, then in the outcome, in the image of Laplace transform, you are shifting the argument. What did we call this rule? Let's have a look. It was rule number 3, shift in the image. Yeah? Shift in the image. That's why it was called that way. Okay? However, when you look at t, e to 3t, it's not that we have this extra exponential. We can perhaps see it as extra t. So let's try it again. Laplace transform of t, e to 3t, Heaviside function, is, so in our first attempt, we focused on t. Now we focused on e to 3t. That will be our f, so to speak. there is an extra t. Do we have a rule for extra t? And the answer is yes, it's rule number 4. And rule number 4 says, if you have an extra t in front of your function, you can do it in the following way. First of all, you just do the Laplace transform of your original function, Laplace of t. So it will be the Laplace transform of e to 3t. When you are through with it, you differentiate it with respect to s. How many times? As many times as you have t over here. T to 1 means I differentiate it with respect to s just once. Why with respect to s? Because that's a new function. Laplace transform, that's the image. It has s as the variable. Finally, I should modify sign. Negative 1 to n. N is 1, so I put minus here. Okay? So I just interpreted the rule number 4 as it applies to this specific situation. I have e to 3t as my key function that I know how to handle. An extra part. Getting rid of the extra part means I have to do some work. By the way, notice that if the extra part is multiplication by the variable, this transforms into differentiation. And when you look rule number 6, it says, rule number 5, it says that differentiation transforms into multiplication by variable. So there is like a symmetry up to a sign, up to some little details. But there is some sort of symmetry happening. Anyway, let's finish it off. I should be taking derivative of the Laplace transform of e to 3t, which is in our dictionary, and I happen to remember it. It looks like that. Now we differentiate with respect to s, and it will be negative 1 over s minus 3 squared, which is 1 over s minus 3 squared, which is exactly what we obtained before, and we are not surprised because it's the same starting point, so we should end up with the same place at the end as well. Wonderful. So this is how you apply those rules. Let me show you a few more examples. When you look at the dictionary, you will notice that cosine hyperbolic is missing. Perhaps because it's not as popular, or perhaps because it's so easy that we don't need to remember it. What is cosine hyperbolic? Well, this is definitely 1/2 of e2 omega t plus e2 negative omega t. That's what the definition says. Okay. Laplace transform is linear. I'm taking out 1/2, and I'm applying Laplace transform to e2 omega t and e2 negative omega t, which means that I have 1/2. The exponential, I remember it. It's in my dictionary. No surprise there. Here the constant is negative omega. So it's s minus minus omega. And now I'm going to use common denominator for these two guys. This is s minus omega, s plus omega. And when I use common denominator, s plus omega, s minus omega, I will get 2s. And the final result is s over s squared minus omega squared. That's the Laplace transform of the hyperbolic cosine. And just out of curiosity, let's have a look at the ordinary cosine. Ordinary cosine, when you do a Laplace transform, is s divided by s squared plus omega squared. The only difference is here in the sign. And now you can make a guess, looking at the chart, what will be the Laplace transform of sine hyperbolic. And I'm pretty sure that your guess is correct. Last example. Laplace transform cosine of pi t. And again, there is Heaviside function. Heaviside function. Always there is a Heaviside function. We see it there. We just didn't write it. Now you may say, oh, wait a second, this is easy. We just substitute in the dictionary. That's true, technically. but that would be too boring. And life is too short to do boring things. So let's try something else. What is cosine pi t? Well, for instance, it's sine pi t differentiated. Is that right? Not quite. I still have to divide by pi, and now it's correct. Okay? Well, let's see. First, I get rid of 1 over pi because Laplace transform is linear. See, that's one of the advantages of the script L notation. It allows me to do things step by step. I can delay some actions for later. I'm delaying handling the derivative for later because I don't want to do 2 rules at the same time. I could do it, but it's safer like that. Okay. Now it gets interesting. Laplace transform of a function that I like, but differentiated. There was a rule. I actually proved the rule. And it's over here, the second last line. If I want to transform derivative of my function, I just transform the function itself. That's what the rule says. So I'm just transforming sine by t. But after I do it, I have to multiply it by s. And I have to subtract limit of my original function at 0. Let me write it down. Limit t going to 0 from the right, sine pi t. And this is all multiplied by 1 over pi. I have to be careful. 1 over pi applies to this whole thing, and therefore I have to use brackets so that 1 over pi applies to the whole thing. Okay. 1 over pi. What is the Laplace transform of sine pi t? And the answer is here in my dictionary. It's pi divided by s squared plus pi squared. But I shouldn't forget I'm multiplying it by s. And I'm subtracting. Sine t, when I put t to 0, is just 0. And now there will be a little bit of cancelling, and I'm getting s over s squared plus pi squared, which is exactly what I expected right from the start. Okay? So we just saw how the grammatic rules are applied, and that's about it. We can sort of imagine that we know how to do the Laplace transform, how to transform popular functions, and there are modifications using the grammar. Which means that we can take a differential equation, which is sitting here in this world, transform it into the new world of functions with s, and derivatives change into multiplication. So the new equations will be algebraic. We can solve them. We solve them there, and now we want to go back. And this is where it gets interesting. Unlike Fourier transform, we don't have some nice integral that we could use to go back. That's the price that we pay for screwing up with Fourier transform. With complex unit, things were nice at this stage, but really ugly at other stages. So it's a trade-off. Now we have really nice dictionary, really nice grammar, but it's difficult to go back. In particular, notice that if I take the function 1, or the Heaviside function, it moves under the Laplace transform to 1 over s. If I take this function and I change it at a few points, then the integral in the definition of Laplace transform cannot recognize that, because we know that integral doesn't care about change at a few points. So this new function, which is definitely not the Heaviside function, will be also transformed into 1 over s. And you can imagine that I can modify the Heaviside function in many ways. So there are infinitely many functions, and they are all sitting here in this space L0 because they are piecewise continuous, definitely. They are bounded by some exponential, definitely. So there are infinitely many functions that are all transformed using Laplace transform into 1 over s. And this is really bad because how do you go back? That sucks. officially. Here is a theorem. When you have two functions in L0 which are sent to the same image under the Laplace transform, then yeah, they should be the same most of the time, but only most of the time. There could be countable set of isolated points where they differ, which is bad. So we don't know how to go back. But when we decide that we want to go back to something nice, then there is just one way. That's the second part. If f and g are continuous from the right, then they must be the same if they go to the same Laplace image. In other words, if you start with 1 over s and you want to go back, there are infinitely many functions that look essentially like that. But when you ask, I want continuity from the right everywhere, then this is your picture. There's only one that works. And it's this one, the nice one, because continuity from the right means you are picking a nice function among functions which are perhaps not so nice. Okay? So this is actually sort of like a mathematical justification that we can go back to something nice. But we are still not learning how to go back, because there is no formula for going back. Fortunately for us, when solving the differential equation here in this world, we typically come up with rational functions. And for rational functions, we can go back. First of all, if you get lucky enough, and that's the part on the left, if you end up with some basic expressions, you know how to get back. And this is essentially the first chart, the dictionary, just written the other way around. So this is not surprising. If you remember the dictionary, you also remember the dictionary for the inverse transform. Second, there are some rules. And these are, again, the rules that we had before, just we look at them from the right to the left. We read them in the opposite direction. So again, nothing surprising. And the most useful rule is number 1. When we are going back, it's a linear process again. And finally, here's the theorem. If you end up with a function here, which is a rational function, a ratio of two polynomials, then you can split it into partial fractions and use it to get back. And that's it. That's all that we need. So let's go back to the list of known transformations. This is the list that I want to see. And let's have a look at some differential equation. Finally, we are getting there. We have an initial value problem here, a differential equation, order 2, and 2 initial conditions at the same time. So this all fits beautifully. Just out of curiosity, this equation is linear, obviously, with a special right-hand side. So characteristic numbers, they would work. The undetermined coefficients method, well, the guessing method, it would work as well. We could solve it in half the blackboard, perhaps. And perhaps that would be a good idea. But we will try something else. We will apply Laplace transform to this equation and move it to this other world of functions. Okay? Right now, this equation lives in the world of functions with variable t, and hopefully it also lives in the world L0. L0, these are the functions where we can apply Laplace transform. Sine function, is it piecewise continuous? Definitely. Actually, it's continuous. And it does not grow faster than exponentials. So this definitely belongs to L0. In fact, we know how to transform it. So that's great. The left-hand side as a whole is the same. So definitely it's in L0. We can transform it. Here we go. So we transform on the right. We transform on the left. Now let's break it. On the right, I'm going to call on my dictionary 1 over s squared plus 1. On the left, I'm going to call on some rules. This is a linear combination of two objects, of two functions. And Laplace transform is linear. So here we go. I just apply Laplace transform to y double prime. And then I 4 times apply Laplace transform to y. And this is where it gets interesting, because I don't know whether the function y by itself and the y second derivative are from L0. Can I actually apply Laplace transform to the individual parts? And the answer is we don't know. So we are going to be optimistic now. We are going to say, okay, let's assume for the moment that there is a function y from L0 which does solve my equation. And then I will try to find it using this approach. And if I do find it, then it was there. And if I don't find it, then tough luck. Okay? So, let's move on. Let's go on with it. Laplace transform of y second derivative. For that, we have a formula. It says, instead of applying Laplace transform to y second derivative, just apply it to y. Easy. But you will pay for it. How? First of all, this is multiplied by s square. And now, we have to go through the tail of the rule. So we subtract s times, and we substitute 0 into y, but it need not be continuous. So this has to be done as a limit, in general. And then we subtract y prime at the origin, again as a limit. So that's the rule for the second derivative. Then there is 4 times Laplace transform of y, and we have this right-hand side. Finally, s squared. What is Laplace transform of y? That's some function which perhaps does not even exist if we are pessimistic. But we are optimistic. We imagine that it does exist. I don't know what it is, but I can give it a name. And not surprisingly, I'm going to call it ys. So it's over here, but it's also over here. Here we go. What is y at 0? Well, remarkably, I have my initial conditions telling me exactly this. So this is very nice. The first derivative over here. So you can see how the initial conditions nicely fit for the Laplace business. We will get to it later. 4 times ys, that's just my notation, is equal to 1 over s squared plus 1. So what did just happen? Our original equation hopefully lives in the world L0. Therefore, we can apply Laplace transform to the equation, and we moved it into this other world of functions, functions with variable s. And there the equation looks like this, and it's no longer differential. It's an algebraic equation, so we can solve it. Wonderful. I isolate ys, and I factor it out of the 2 terms, s squared plus 4, and I move everything else to the right. 1 plus 13s plus 1 over s squared plus 1. Is that right? I think so. Finally, ys is 1 over s squared plus 4 plus 13s over s squared plus 4 plus 1 over s squared plus 1 s squared plus 4. That's a solution. We just solved our problem in this other world of functions. Now we need to go back. And as I commented before, we have no formula for that. We have to hope for luck. We had this theorem which told us that if we get a rational function, this is a rational function, we can use partial fractions and then the dictionary, essentially. That's the strategy. For instance, s divided by s squared plus 2 squared, I can see it as a formula for cosine. Well, okay, not 1, but 2 divided by s squared plus 2 squared, that's the formula for sine. Can I create 2 here easily? So I don't worry about this part. This part bothers me. But that's the partial decomposition that we had in the theorem. So I have to recall some stuff from calculus again. I mean, this is really turning into review of the whole calculus course. And perhaps not everybody is all that happy about it. I mean, I can imagine a while ago, when I introduced integration by parts here, some of you were not all that happy. And this is perhaps pushing it even farther. Okay, how do we do that? Well, we have to use common denominator to work out the numerator and then compare it, and we get 4 equations with 4 unknowns, something like that. Which I'm not all that crazy about, quite frankly. Now, there is a limit trick which helps. And if I use this limit trick, I'm fairly sure that A should be 0 and C should be 0. And if you don't trust me, you do it properly. You do the complete partial fractions decomposition. But I'm pretty sure that this is true, which simplifies my life in the next stage. So I am going for the common denominator. And assuming that A is 0 and C is 0, things become much nicer. bs squared plus 4b plus ds squared plus d. And now I compare the numerators, and I can see that there are no s squares, but on the right, s squared is how many times? B plus d times. And then there's this absolute term, which happens to be 4b plus d. So it's a nice set of two equations with two unknowns. We should be able to handle that. For instance, I take the first equation and subtract from the second one. And I get 1 is equal to 3b. So b is 1/3, and d from the first equation is negative 1/3. Okay, let's go back. ys is 1 over s squared plus 4 plus 13s over s squared plus 4 plus, okay, 1/3 over s squared plus 1 minus 1/3 over s squared plus 4. Are we getting there? I think so. We are almost there. So let me start from the left. ys is, here it is once, and I'm subtracting it 1/3 times, so it will be 2/3 times over here. 2/3 times s squared plus 4 plus 13 times s over s squared plus 4 plus 1/3 time 1 over s squared plus 1. That looks good. I think I'm ready. Let's go for it. This is a function in the target space for Laplace transform. We want to go back. We know, we talked about it, that for each of these guys, there are infinitely many functions which are transformed into them. But we choose just one, the one which is continuous from the right, the one that we like. And suddenly, things are unique, and we can sort of talk about inverse Laplace transform. This is not quite proper. We would have to do some work. But OK, let's go with that. Yt is, OK, I can see here s squared plus 2 squared, s squared plus 2 squared. So to use my dictionary, I would really love to see number 2 on the top. So I will borrow it from here. I will shift number 2 from this numerator to this numerator, and suddenly I get exactly the thing that I need for sine. 1/3 sine 2t. So far, so good. 13 times, and again, cosine 2t. Wonderful. So far, so good. 1/3 time, and that's exactly the image for sine t. And we are done, and let me put t greater than or equal to 0. Now, properly, and we will get to it in the next lecture, actually, I should be putting Heaviside functions next to these guys. But another possibility is to just restrict our attention to t greater than or equal to 0. And this makes perfect sense from application point of view, because this event started at time 0. So there is no point in asking what happened before that. We don't know. Everything started at time 0, and this tells us how it went. Okay? That's it. We just solved our system, our initial value problem using Laplace transform. Wonderful. And it wasn't so bad. I mean, apart from the partial fractions business, and it wasn't so bad either. So yeah, it works. It's nice. Okay, some good questions. First good question. It's quite clear at this stage that we need initial conditions to be able to apply Laplace transform. What if somebody gives us just a differential equation and wants us to find a general solution? And the answer is, well, we just introduce initial conditions on our own. And instead of putting some numbers, we put a and b. Numbers a and b, they will appear over here, a and b. And they will survive this whole trip. And they will appear over here, a and b. Which we can guess easily, because if you look at characteristic numbers, plus or minus 2i, sine 2t, cosine 2t, that's the fundamental system. With a bit of experience, you just look at it and you can see it, okay? So this is not surprising that A and B appear over here. We would get a general solution. So yes, Laplace transform can find also general solutions by using this trick with A, B, C, D, whatever initial conditions. Okay, second good question. What type of differential equations can we solve using Laplace transform? Well, let's have a look at it. First of all, when we are transforming the left-hand side, we were using some rules, and when we look at the list of rules, it's not exactly rich. So essentially, unless you want to end up in big trouble, you want to stick to linear equations, for which we already do have an approach using characteristic numbers. So we are not really gaining anything, are we? How about the right-hand side? Well, we need to be able to transform it. We have a look at our dictionary. Sine, cosine, exponential powers, that's exactly what we can guess. Yes, we can do guessing for all these guys and their combinations. So right now, it seems that Laplace transform can solve exactly the same equations that we can solve using those earlier analytic methods, which is not very encouraging. However, there are some rules in the list that can be used, and we will add more rules to the column, well, one more rule, one key rule to the column on the right. And this will allow us to solve differential equations where the right-hand sides are more interesting, and they are very useful for circuit theory, electric circuit theory. And this will have to wait for the next lecture. This one is already too long anyway. So next time, we will learn how to extend our capabilities to a new type of differential equations, new type of functions on the right, and it will be interesting, it will be nice. And that's really one of the strong points of the Laplace transform. I'm not going to say more, let it be a surprise for the next time. You'll be looking forward to it. Already now, there is a rule in the list of grammar over here. It's not in the short list, it's in this long list, that allows us to solve a new type of an equation that we didn't see before, which are integral equations. So let me just show you one last example, and it will be an easy one, which also shows that the Laplace transform perhaps can do something nice for you. We will need more room. Equations with integrals sometimes appear in physics. We have a function which depends on time, and just to show something for physicists, I'm using physical notation, so the unknown function is x, for instance, a location, position, and the derivative with respect to time is denoted by a dot. One can encounter it sometimes. On the right, over here, we have an integral where u serves as the working variable for the integral, that's the dummy variable, and the real variable, time, appears as a limit. So that's an integral that we know from calculus. The outcome of this procedure is some function which depends just on time. So this all makes sense. One function with time as a variable, another function with time as a variable. And we have an equation. So let's apply the Laplace transform. We lack initial conditions, but perhaps that's a good thing because it's not quite clear what is the actual order or how many initial conditions we need. There is just one derivative, so I would say, okay, first order differential equation, but it's not differential. It's differential integral equation. So what are the rules there? We didn't cover it in class, so let's ignore it, okay? We will see something later on. I'm applying Laplace transform, being optimistic that x is from the space L0. Okay, over here, I'm applying the Laplace transform, and it's a Laplace transform of derivative. Let me switch to this other notation because we are used to it. Then there is 9 times Laplace transform of this type of integral. And on the right, Laplace transform of 0, which is, of course, 0. No problem there. Laplace transform of derivative. For that, we have a rule. Well, we had it in our shortlist. So let's go back to our shortlist. It's the second rule from the bottom. So we should transform just x, which we call capital XS, and multiply it by s, and subtract the value at the origin. And this tells me that we will need one initial condition, and I can make it a general one, A. Okay, I will replace it later on. I just want to show how it works. Then we have 9 times Laplace transform of integral of x. And for that, we need to go to this long list over here, and down at the very bottom, almost, rule number 6, integral of pre-image. If you want to make a Laplace transform of integral, we just transform the argument and divide it by s. So we transform the argument, which is capital X, and we divide by s. Now notice, when we are Laplacing, so to speak, derivative, we multiply by s. When we are Laplacing integral, we are dividing by s. Opposite procedures, so to speak. It sort of makes sense, yeah? It's definitely easy to remember, let me put it that way. So, we have an equation, let me replace over here, sxs minus a plus 9, 1 over s xs is 0. And that's an algebraic equation. We can solve it. Let's go for that. Well, let's see. What can I do? You know what? I'm going to multiply everything by s, because I don't like division. So I'm going to multiply this by s, this by s, this by s, and I move this to the right. As. And on the left, xs is multiplied by s squared plus 9. So xs, and that's capital X, is as over s squared plus 9, which is a times s over s squared plus 3 squared. Why did I do it? Because, well, I think you know where I'm going. Let's go back to the short list. Here we go. I'm aiming at the cosine. Cosine where omega is 3. So xt, that's my solution, is a times cosine 3t. T greater than or equal to 0, and I'm done. Wow. I just solved an equation with derivative and integral. And I have found a general solution. Wonderful. Another victory for Laplace transform. Now you may say, oh, wait a second. Why don't I simply differentiate this equation? Well, x prime plus 9 integrals 0 to t x u du is 0. By differentiation, I get x double prime plus 9 times, and by the fundamental theorem of calculus, when you have an integral of this form and you differentiate, you get just x. And that's a fairly simple linear differential equation. You find lambda is plus or minus 3i. So the general solution is a cosine 3t plus b sine 3t. And you are beginning to see the problem. It's something else. So when you are in doubt, you simply check. You take this formula, you substitute it into the original equation, definitely into the original one, not here. You substitute into the original equation and you find that it doesn't work. Actually, the cosine part will disappear. The sine part, that's the trouble. So you can use common sense and say, okay, by checking, I find that this part should be gone, and this will be my solution. Does it work? Essentially, yes. You see, the problem is that this operation, differentiating a differential equation, is not equivalent. How do I know? Well, let's have a look at it. Here we have an equation. We solved it. And now we try to go back. How do we go back? Well, by integration from 0 to t. And when we integrate between 0 and t, going this way, we can write it as x prime plus 9 integrals from 0 to t x u du is equal to c. And that's the problem. So this function with two components, it does solve an equation, but it solves this equation with c some constant, any constant. Here c is 0, and that's why the sine part is gone. Okay? So yes, you can actually use common sense and the usual approach to solve equations with integrals and derivatives. It does work, but one has to be careful, and do some reasoning. When you apply the Laplace transform, you get exactly what you need right away. Another big advantage of Laplace transform is that a computer can do it, computer algebra system, because it just goes by the rules. It's easy to teach a computer, a good program, these rules, and then the computer can just apply them. And this is actually something that can be made into an algorithm. So that's also nice. And that's all for today. So as of this moment, hopefully you understand how the Laplace transform works. You can see the mechanics, you can see the ideas, you can see the tricks. And essentially, for practical work, you just need to know this, essentially this slide. Okay? But it's good to understand where it comes from because it helps in situations which are not, let's say, straightforward. Okay, see you next time.